We've all experienced the frustration of a forgotten name or a misplaced set of keys. Yet we can also recall with vivid clarity events from our distant past. This dichotomy of memory, its ability to both preserve and fade, has fascinated scientists and philosophers for centuries. How is it that some memories last a lifetime while others vanish like whispers in the wind? Our memories are not static entities, but rather dynamic constructs, constantly being shaped and reshaped by our experiences. They form the very foundation of our identity, connecting our past to our present and shaping our future. Understanding the mechanisms that govern memory formation, retention, and retrieval is crucial, not only for unraveling the mysteries of the human mind, but also for developing treatments for memory-related disorders that afflict millions worldwide. The quest to understand memory has led researchers deep into the intricate workings of the brain. They have discovered that memories are not stored in a single location, but are distributed across vast networks of neurons. These networks are connected by synapses, the tiny junctions where signals are transmitted between neurons. The strength of these synaptic connections is crucial for memory formation and retention. Recent research has also begun to explore the possibility that memory may extend beyond the brain itself, involving other systems in the body. This emerging field of embodied cognition suggests that our memories may be encoded not only in our neural circuits, but also in our muscles, organs, and even our genes. One of the key mechanisms underlying memory formation is long-term potentiation, or LTP. LTP is a process by which synaptic connections between neurons are strengthened, making it easier for them to communicate with each other in the future. Imagine a path through a forest. The more you walk the path, the clearer and more defined it becomes. LTP is like that well-trodden path, strengthening the connection between neurons that are activated together. When we experience something new, whether it's a new face, a new piece of information, or a new skill, specific groups of neurons in our brain are activated. If this activation is strong enough or repeated over time, it triggers LTP. During LTP, the synapses between these neurons undergo structural and functional changes. They may grow larger, release more neurotransmitters, or become more sensitive to incoming signals. These changes make it more likely that the same group of neurons will fire together in the future, strengthening the memory trace. LTP is essential for forming long-term memories. It provides a cellular mechanism by which our experiences can leave a lasting mark on our brains. However, LTP alone is not enough to explain the complexity of memory. Once a memory is formed through LTP, it doesn't simply sit passively in the brain. It undergoes a process of consolidation where it is stabilized and integrated into existing neural networks. Think of it like wet cement. Initially, it is malleable, but over time, it hardens and becomes more permanent. During consolidation, memories are transferred from the hippocampus, a brain region involved in forming new memories, to the cortex for long-term storage. This process can take days, weeks, or even years, and it is influenced by a variety of factors, including sleep, stress, and emotional arousal. However, even consolidated memories are not set in stone. When we retrieve a memory, it becomes temporarily labeled, meaning it can be modified or even erased. This process is known as reconsolidation. Imagine taking out a book from a shelf and then putting it back. You might accidentally put it back in a slightly different position or even on a different shelf. Reconsolidation provides an opportunity for us to update our memories with new information or to weaken the emotional intensity of traumatic memories. It also highlights the dynamic nature of memory, showing that our memories are not fixed recordings of the past but are constantly being shaped by our present experiences. For memories to last a lifetime, they need to be maintained over long periods. This is where PKMzeta, a molecule found at synapses, comes into play. PKMzeta acts like a molecular glue, helping to maintain the strength of synaptic connections that are essential for long-term memory storage. Imagine a bridge held together by bolts. PKMzeta acts like those bolts, ensuring that the bridge of memory remains intact. Without PKMzeta, memories can weaken and fade over time. However, PKMzeta doesn't act alone. It works in concert with other molecules, including KIBRA. KIBRA is like a synaptic tag, marking specific synapses that are involved in long-term memory storage. It interacts with PKMzeta to ensure that these synapses remain strong and stable over time. The discovery of PKMzeta and KIBRA has provided new insights into the molecular mechanisms underlying long-term memory maintenance. It has also opened up new avenues for developing treatments for memory-related disorders. For example, drugs that enhance PKMzeta activity could potentially help to strengthen memories in people with Alzheimer's disease.